Okay, we can start. Just remember, couple of things. So I posted an announcement a few minutes ago. Basically, my plan is today I'll finish the material for the course. Wednesday, then I'll do a review session with you, record it. I have another class on Thursday. I'll do a different set of problems with them and also record it. So that way you get two review sessions. Um, I'll do like at least for the final one problem. There will be one problem from each review session, so you have like some incentive to watch them or go over the problems I do in both classes, and then there will be three other problems. Again, this is on the announcement. One will be the exponential of a 2 by 2 matrix. I like those problems. Another one will be this conic section stuff we did last week, and another one will be like kind of similar to what I'm about to do today. So that more or less gives you 5 out of the 8 problems, and then maybe I'll have one from the PDF, another one, and that I take from that list of problems, and then like at least 6 out of the 8 should be relatively familiar territory, and then like yeah, the other 2 may be new, but it's usually when I do new problems, they just change a little bit the numbers that we have done in class. So they would, I mean, more or less the exam will be relatively predictable. Um, and if you do all the problems and the assignments and all this stuff, yeah, you'll be good to go for the final. Yeah.
Is there a lecture next Monday?
Oh, right. I forgot to say that. So my plan for Monday of next week would be more like office hours. So you can show up if you want to ask me something specific, but if you're good to go, then you don't have to come. I won't give any sort of lecture. It won't be review, but like, if many people have the same question, I will just answer it on the board or whatever. I'll also give you office hour. I'll probably have some office hours, on that week of finals, like on Wednesday. I'll send an announcement, later about that. But yeah, that was my idea. So Monday is more like, come if you want to ask me something specific, but if you don't, then, you don't need to come. Yeah.
So is the final gonna be like all 3 hours, or is it gonna be like 2 hours?
Well, you do have 3 hours. I'm designing it more like for 2 because I'm doing it like 8 problems, so it will be a little bit over like the usual midterms, right? So I'm like, yeah, I'm thinking more of it like a midterm plus 1/3 of the time, yeah. So more like 2 hours. Uh, Even some people here have left a bit earlier than that, but I'm just saying, yeah, I don't want that a 3, like, you should have a lot of extra time to double check everything, make that everything.
Is final in here?
Yes, I believe so. I think in your case is, your day for this class was May 9th, but you can check the, yeah, if you are listening on the video and you heard my other class, check your Canvas assignment. But yeah, this class is May 9th. The other class I think was May 4th. But yeah, it should be on this, same, classroom. Anyone else? Okay. So before I tell you the last topic that I want to discuss, let me just remind you a little bit of what we were doing at the end of last time. So last time we were talking about this, orthogonal complement to a vector space. So the idea is that V is, or I could call them W, but V is a vector space you care about. So V is a vector space, and V paired, which is called the orthogonal complement. This just consists of the vectors which are perpendicular to every single vector of V. That's like the important condition. So these are the vectors to every vector of V. Is that okay? So just to make some pictures. In 3 dimensions. Like one example could be the a vector space of dimension 2. Which would be like a plane. And the orthogonal complement would be all the vectors perpendicular to that plane that ends up being a line. So you draw a line in space. The idea is like this line should be making like a 90-degree angle with a piece of paper, right? Which is the plane. So this would be B perp, and the dimension of B perp would be 1. Okay. Another situation you could have is, for example, it kind of the reverse of this one, where like you had like now B is like a line. And B perp would be then all the vectors perpendicular to this line, which actually makes up a plane. So now B perp would be 2 of dimension 2. Okay. And I think someone may have asked this at the end of last class, but if you think about it, like this is something of dimension 3, this one has dimension 2, and this one has dimension 1. This still has like the bigger space has dimension 3. Now this one has dimension 1, and this one has dimension 2. So what's actually happening is that the dimensions add up to the dimension of the bigger space, the one that they belong to. So right, 3 is 1 plus 2, and 3 is also 2 plus 1, right? Things like that. So I will write it down in a moment. But the dimension of B plus the dimension of B perp actually always adds up to the dimension of the larger space. So so first, one thing. So obviously this won't be a perfect picture because I can only draw things kind of like in 3 dimensions. But if you have something 4-dimensional, so imagine that instead of x, y, z, you have a 4th axis w. I cannot even draw it like accurately, right? Because we don't have enough room to draw things in 4D. But imagine this is in 4D, right? So the vectors are now like x, y, z, w. So 4, right? 4 is also, for example, 2 plus 2, right? So what you could have is like a vector space, which is of dimension 2, which actually would be like some sort of plane. And then you would have like another, the orthogonal complement, it would be of dimension 2 as well. So it would look like another plane, right? So I think that you could have, like, for example, in 4 dimensions, it's 2 planes which are mutually perpendicular to one another, if that makes sense. Of course, you can have other crazy things in 4 dimensions. You could also have like a line, which is 1, right, 1-dimensional, and then the complement should be 3 because 3 plus 1 equals 4. So the complement to the line would be like a kind of like a cube or something that looks like our ordinary space. So obviously, and then if you have something of dimension 10, like the total space, then well, 10 is like 9 plus 1 or 8 plus 2, 7 plus 3, 6 plus 4. Like, you know, there are many different combinations of 2 numbers, positive numbers that add up to 10. So for all these examples, like there would be like a corresponding vector spaces of those dimensions with their orthogonal complements. Is that making sense? Yeah.
If the subspace spans the entire vector space, that split the dimensions of perpendicular, that just be 0.
Yeah, if V happens to be the total space, or however you want to call that, something that's perpendicular to everything is just a 0 vector, so the orthogonal complement is 0. which is zero dimensional in a way. Although, right, like usually, of course, for actual examples, I'll give you interesting things like that they don't collapse completely to all or nothing, but yeah, that does work for that special case. Is that making sense? Any other questions? So what I was writing here, like, or what I was saying, a few moments ago is that the dimension of B plus the dimension of B curve equals the dimension of the larger space, or if you want to say it in a more concrete way, it equals the number of entries of your vectors. So and then what did I say last time about how to find P perp? So let me remind you how this works. You first find a basis for B, okay? So step one is to find a basis for B. Step two is to make a matrix A whose rows are the basis vectors of B. So whose rows basis vectors of B. In particular, not that it's super important at the moment, but this is telling you that B is the row space of A, right? Because what does it mean to be the row space? Are linear combinations of the rows, right? But if the rows are the basis for B, then almost by definition, like a vector like B is just like the linear combinations of the rows of A, so it's just the row space. Okay. Kind of it should look circular because it's kind of is, but you'll see why in a moment. That's at least kind of interesting to bring mention explicitly. And then the P perp is the null space of this matrix. So that brings us back to finding null spaces, which we'll do in a couple of minutes. Is that making sense? So what this says, this is the only reason why I wrote this, because I'm not really going to use this a lot, actually ever. But what this is saying is that the complement, the orthogonal complement to a row space is a null space. That's called the fundamental theorem of linear algebra. So, but again, I won't really use it, but let me just write it down. I won't use it explicitly in this way, but it's kind of nice to know. Okay. And then what would be the complement, the orthogonal complement to the column space? Well, the column space, if you remember, is the row space of A transpose. And now we know that the complement to a row space is like the null space. So it's just a null space of A transpose. Okay. So I mean, like what this says is that it gives you two formulas for how to find the complement to a row or column space. Which again, I won't ask it directly in terms of a matrix. I'll ask it more like find the orthogonal complement to a vector space, because I prefer to think about it in terms of vector spaces. But you can also think about it in terms of matrices, since that's more like your thing to think about this in terms of matrices. Questions about this? Okay, so let me do an example about this, and then we'll move to this orthogonal to this projection matrices, which is the last topic I want to do today. So let me I think it will work. So let's say I want, if not, I'll fix it in a moment. I want to find the perf for you. So if you look at the steps, the first step is to find a basis for B. Maybe you remember this from before, but like the way to find a basis for V for a vector space, well, you just play with the equations that you have. And so if you take a vector X, Y, Z, W, then X, I will write everything in terms of X and W. That's why I wrote it on purpose. So x, y is w minus x. Okay, this should be fine, I think. And then c is 2x plus w, and w is w, right? That making sense? And then we break this into the stuff with x and the stuff with w. Yeah, this is fine. This will work. I mean, I wanted something kind of not too silly. So the bases for V are these vectors V1 and V2, right? Is that making sense? Any questions up to this point? Is that okay? So that's the basis for V. Step 2 is just to make a matrix whose rows are these basis vectors, so you can write that down. Okay. That making sense? And then step 3 is to find the null space of this matrix. So to find the null space of this matrix, if you want, you can reduce it first a little bit. So you can do like how to reduce it? You can do row 2 plus row 1 into row 1, right? And you end up with 1, 0, 3, 1, 0, 1, 1, 1. Right? And so from there, because it's row reduced echelon form, it is easy to read off the conditions for being in the null space. The conditions are that x plus 3c plus w should be 0, and that y plus z plus w should be 0. Okay, so that gives you like x and y in terms of z and w, right? Is that making sense? So far so good. And now we apply the same logic as before. If you take a vector x, y, z, w, and then you break it into the stuff with z and the stuff with w. And that's what I'm calling the vector u1 and u2. So these two vectors are a basis for V perp. Is that making sense? For a second. questions about this? And what that means is that if you take the dot product between this vector and any of the two basis vectors, it will be zero because they're perpendicular, so you should check it out. And if you take the dot product between this vector and any of these two basis vectors, it would also be zero, right? So each vector there is perpendicular to every vector there. I mean, it's actually vice versa, right? Because if U is perpendicular to V, then V is perpendicular to U. So it's like a symmetric relationship. It goes both ways. But the important thing is that every vector on that side is perpendicular to every vector on the other side. So this actually corresponds to the picture that I kind of was trying to draw, because the vectors have dimension 4. So you have each of these two is actually like a plane in dimension 4. So you have like two planes which are mutually perpendicular. Okay. Is that making sense? Any questions about this? Okay, so yeah, moving to the last topic for the semester. So let's talk about projection matrices, which are very useful. So this has to also keep around. So what's the idea here? The idea here is that you're going to have a vector space W, right? And you have like some random vector. Like this one. And now what we're going to try to find is the shadow. Again, we go back to this shadow business. We're going to try to find the shadow that this vector makes on on this piece of paper or on this plane, right? So I mean, again, imagine that you sort of have like a light bulb, and then you're going to see like the shadow that this vector makes. So we're trying to find like a vector like that looks kind of like this, if that makes sense. This shadow is what I'm going to call P sub W of B. Is that making sense? So this, I mean, I'm trying to define it in a way that's more geometric. So it's more like a conceptual question at this point. So imagine that I give you a vector that already happens to belong to the what looks like the plane. I mean, it doesn't need to be a plane. I'm just trying to do like a picture that's more like easy to represent. It will have higher dimension, this W vector space. But let's say it was like some sort of plane. What would be the shadow of a vector on the plane? What should the shadow be?
The vector itself.
It should be the vector itself, right? Is that everyone okay with that? So there should be B So this thing, what got this, whatever this is, it should leave, do nothing to the vectors that already happen to be on the vector space we care about. You just leave it alone. And what happens? What happens if you choose a vector that lives in the complement, in the orthogonal complement, right? Now this is a vector perpendicular to everything. So what should the shadow be? It should be zero, right? Because like think of the plane as like the actual floor, and if this were like the actual floor, then like a vector perpendicular to it would be like kind of completely vertical, and so the shadow it should be just like a dot, right? Like the zero vector. So this should become zero. Does that make sense? So this kind of gives us like a formula when the vector happens to be on W or on W perp. But the thing is, since the dimensions of these two vector spaces add up to the dimension of the total space, that kind of gives you a formula for any other case. Because what's going to happen is that this vector, any other vector, is going to be, it's kind of like a sum of a vector on the shadow and a vector on V perp. Let's call this WV on W perp. So if you look at this picture, what I'm trying to say is that V equals, let's call this VW. Right? So if you wanted to know what PV is, VWV is, well, that's going to be PW of VW plus VW perp. But this is PW of VW. So since this one lives on W already, the projection does nothing to it. So the first one is just going to give you the same vector back. And since this one is perpendicular to W, then this one gives you zero. So what I'm trying to say is that once you know what I'm trying to say is that once you know the formula in these two cases, everything else follows by taking appropriate linear combinations. So really, I'm about to give you like a more concrete formula anyways, but I'm just trying to say that many times the way you can try to define like a matrix is kind of define it for vector spaces where you kind of know what the right definition should be. And if the vector spaces add up in dimension in this way, and they're complementary in some precise sense, then it kind of forces the definition for any arbitrary vector just by using a like linearity property of the matrices that you can just distribute like this operation around. So that's just to say that I mean you don't have to pay too much attention to this. It's just to say that once you know that the formula for these two special cases, you kind of know it everywhere else. Okay. The important thing is actually to understand this, okay, because it will be used in a couple of minutes. So that's really the important part. So if you ever take multivariable calculus, again, like you have done like these projections when it is one vector onto another. This is the generalization of that when they're like when it is not like the shadow along a vector, but rather the shadow like along a plane or a higher dimensional space. So let me give you some facts about this projection matrices. Like the majority of them are proven on the PDF if you want to read it. But the proofs are not, I mean, they're not too complicated, but also like it just takes a little bit of time to get used to what sometimes these proofs in linear algebra seem too simple that you are not sure if you're proving anything. So if you want to read it, then it's on the PDF, but yeah, the proofs themselves are not too bad. So the first, which is like a formula, but that's not the formula that I'm going to use, so, but it's nice to have it around, is that if you have an orthonormal basis for V, or for W, sorry. Then once you have an orthonormal basis for W, you can like actually write down what this should be. So that's like one version of the formula, although it's okay, but it's not how I want to will find this formula. But it does work. Okay. What's more important? Well, let me give you a second to write this down. Okay, let's think about this for a second. So what should be the square of this matrix? So what that means is like, remember, or this operation. This operation takes the shadow of a vector, right? So you have a vector, you apply this operation once, you take it, you find its shadow, right? And now this is saying apply twice, right? So it's like taking the shadow of the shadow. So what should the shadow of the shadow be? It should be itself, right? There's nothing else to do. Like you kind of like already found its shadow, like, you know, it like applying this multiple times cannot give you anything new. So like the matrix way to say that is that P square equals P in the sense like it does nothing to apply it again. Is that making sense? So shadow of a shadow is a shadow, right? A shadow of a shadow of a shadow is a shadow. So it doesn't matter how many times you try to apply the shadow operation. After one time, it already did everything that it could do for you. So I mean, again, it's kind of like if you understand the definition, it's kind of easy to convince yourself of that. If you thought, if you think about it from this formula, it would be a mess to prove it just from this formula. So it's kind of that's why it's useful to have like both points of view, like what's the actual formula versus what's is this thing doing, right? Again, not too difficult to prove, but you can check it on the PDF. What's really useful about that is that not only is the square of the matrix itself, but this also happens to be a symmetric matrix. And PW, and this is very useful, important information. Meaning that PW transpose is PW. So it's a symmetric matrix that squares to itself. So it has a lot of like cool properties. So in fact, okay, this goes back again. Symmetric matrices are kind of like at least in the category of things you could be if you're a matrix. Being symmetric is one of the best things you could ever be. So what can you say about the eigenvalues of a symmetric matrix? What did we mention? Well, I mean, not well. The eigenvalues are just numbers, so it's you wouldn't think of themselves as being linearly independent or not. Like the eigenvectors would be perpendicular, for example, for different eigenvalues. But it was more, I mean, or let me rephrase the question. What did I say about symmetric matrices that's very important? Right, like they are always diagonalizable. In fact, with a orthogonal matrix, if you remember that as well. So first, like the thing about eigenvalues that I wanted to say is that they would be real. Like again, like that doesn't matter too much in this course because in this course, like we're only working with real numbers. But I'm just saying like you can never find complex numbers for these matrices. Okay, so but you can even say something more about the eigenvalues. Because since the square of the matrix is itself, that forces what that would force is the lambda squared to be lambda. That's the effect that would have on the eigenvalues. So when is lambda squared equal lambda for numbers, real numbers? When does that happen? When is lambda squared equals lambda? Solve this quadratic equation.
For 1 and 0.
Right, 1 and 0, right? So the eigenvalues are actually lambda equals 0 or lambda equals 1. Okay. Now, where do you usually see the number 0, 1 outside of mathematics? In binary computer science, right? So in fact, you can think of like, usually if you see 0, 1, you can think of this eigenvalue as representing falsity and the 1 is representing truth. And there's a trick that you can do to represent like propositions with matrices. So it's on the PDF, which I always found very fun. So like, for example, like there's like a proposition, like a proposition is something like statement that is either true or false. So the proposition could be like, tomorrow it's going to rain. Presumably that has a truth value, right? So if it doesn't rain, you would assign eigenvalue 0 because the proposition was false. And if it rains, you would assign eigenvalue 1 because the proposition was true. And then you can construct this, what people call truth tables, P and Q or Q, where P and Q are propositions. And they can be represented by matrix multiplications of these matrices and so on. And so, like, there's this thing called Boolean algebra, which is what like people use for circuit designing electrical circuits and things like that, which if you want is can be represented by these projection matrices. It's kind of like, I mean, like at this point, it's kind of like a fancy thing, like you're kind of just doing it for fun. The thing is that there had been some approach. I mean, now it's kind of out of like fashion, like not how people do it. But there's like had been like back in the day when people were trying to understand quantum mechanics, they thought, oh, I mean, if you ever go to Wikipedia and enter like the double slit experiment or things like that, there are situations where if you think about it in certain ways, they seem to be violating the rules of classical logic. So there was like an approach to understanding what's going on to say, well, quantum mechanics just obeys what you call quantum logic. And then this quantum logic would have been represented using these projection matrices. So that's kind of actually where this goes back to. But again, that's kind of out of fashion these days. So it's not necessarily the orthodox interpretation of what's going on. But there are many, yeah, if you do like there are many weird experiments in quantum mechanics where if you just think about them like naively, then it's just like, okay, there's something very fishy going on. So like it just seems to violate a lot of common sense assumptions. So, but yeah, you can, if you like, there's one of the, I mean, it's more like a fun problem if someone wants to do it. But on the PDF, there is like a problem that tells you how to construct the truth tables for the and or not using matrices, which is kind of cool to check that it satisfies the usual properties. Um, but anyways, the eigenvalues are lambda equals 0, lambda equals 1. In fact, okay, yeah, we kind of know the corresponding eigenvectors for these eigenvalues. So what are the eigenvectors for lambda equals 1? What does it mean to be an eigenvector for lambda equals 1? That's what this would mean, right? That means that nothing is happening to the vector, right? Because it's 1. So in this formula, where in this formula of the two cases, where is nothing happening to the vector? In the first case, right? So this is saying that if you're a vector that lives in the vector space W, you're an eigenvector with eigenvalue 1. Okay. So those are the eigenvectors corresponding to lambda equals 1. And what is the lambda equals 0 case? Let me put it here. What is eigenvalue 0? Eigenvalue 0 means replacing this one with a 0, right? But if once you replace this one with a 0, you're killing the vector, right? So where in this case, where are we killing the vector? We're killing the vector precisely when you live in W pair. So any vector from the orthogonal complement is an eigenvector for this eigenvalue 0. Is that making sense? So again, like you see, like if you have the right definition for the operation, you can even find a lot of information about the eigenvalues, eigenvectors, without even knowing what the matrix is, right? Like you still haven't even written like a formula for the matrix, and then you can say, well, the eigenvectors are this, the eigenvalues are this, like a bunch of properties. So, and that's going to be useful for the last thing that I have to tell you, which is now this is enough information to write down the matrix expression. Okay. So how are we going to find the matrix? Well, we will use this diagonalization result. So the diagonalization result said that the matrix, any matrix, would be QD Q inverse, right? That's like the regular diagonalization for a matrix. That's what we would write in general. Because this is symmetric, we can improve this and put a transpose here, if you remember. So I'm going to write it this way. So this is like the formula for the projection, and you'll see how this works in a minute. So here, what is going to be Q? Q is going to be the matrix of eigenvectors, right? So there's going to be an orthonormal base. But what are the eigenvectors? Eigenvectors are like from either from W or W perp. So what you do is find a basis for W and a basis for W perp, and those are the ones that you'll do use as eigenvectors. It's just that when we do them as eigenvectors, because we want this to be orthogonal, it has to be of sides orthonormal basis. So the columns are going to be an orthonormal basis for W, followed by an orthonormal basis for W perp. that okay?
Why is it important that it has to be?
Oh, it has to be orthonormal so that I can put a transpose here instead of an E inverse. That's the only reason why it has to be orthonormal. If you didn't care about that, then you could just do the same, but you then have to find the inverse of the matrix. That is a little bit more tedious. It actually, I think it saves you time to do it orthonormal rather than trying to find the inverse of the matrix. I guess in some sense they're kind of equivalent processes that you know, but somehow I always find them more like it just seems more formula. I don't know. It just seems better to do it orthonormal from the beginning.
Look, you find the basis for W per and then W and then, but that just affect the diagram.
No, I mean like I just like right. You could put the basis for W first, followed by the basis for W. That just changes the entries of the eigenvalues on the diagonal matrix. So it is not that you have to do it in this order per se, but just to kind of have like a standard order for people to read it out more easily. But yeah, in general, you know, how you order the eigenvectors is up to you, but it's kind of like elegant to put like the basis for W followed by the basis for W perp or vice versa, but not to scramble them around, like, you know, one of W, then one of W perp, one of W perp, because it just seems a little bit more like disorganized. But it will give you the same answer, like, so it doesn't really matter too much. Right, and so this is going to be diagonal matrix, right? And so it will be one for each basis from W, and then a 0 for each basis vector from W perp. One one for each basis of W for each vector from for each vector from W, and 1 0 for each vector from W perp. Is that making sense? Any questions about this? Okay, now let's apply this in to something concrete so that you see how it works. It's actually very nice. So let's say that W is this vector space. I mean, there's another one on the PDF that I did, but it's way longer and less clear what it gives you because here I can do some pictures, so it's kind of more geometric thing to do. Okay. So on the final, I'll basically ask you like a question that's essentially the same as this one. I will just change the equation of the plane. But I do just want to make sure everyone knows how to find these projection matrices because they're kind of useful things to have around. Okay, so I want to, so first let's start with the picture. How would you draw this? What does this look like? Right. So if you look at this, I mean, if someone hasn't taken yet like multivariable, like you'll see this a lot when you get there. If you look at this, like maybe you would think, well, this is like equation of the line. That's kind of like a reasonable option to answer. So it is a line on the YZ plane, right? But then since there's no x, you kind of get the same copy of this line for each value of x. So what ends up happening is that kind of you drag this line along the x-axis, and that's what makes up your plane. So you end up with something that looks like this. And that's why this is actually like an equation of a plane and not a line, which it is kind of one of those things that you have to get used to, where like one of the variables is not explicitly showing up. But that's kind of how you would, if you were to draw it, really how you would think about this. Does that make sense? So my goal, what I'm trying to do, just to like again remind you of what's going on. What I'm saying is like I'm going to draw a random vector x, y, z, right? And I'm going to give you a formula that will find the shadow this vector makes on the plane. So I'm going to give you a formula that gives you this blue vector. Okay. That's what we're after right now. Okay. So to find the matrix, you need to find Q essentially. Once you have Q, everything else is free. So to find Q, we need the basis for W and W perp. Okay. So how do you find the basis for W? Let's start there. And that's why we started with that at the beginning of class. So what is the basis for W? Oh, remember, we have done this multiple times. To find the basis for W, just plug in Y equals Z, right? And you get what? X times 1, 0, 0 plus Y times 0, 1, 1. Is that making sense? So this would be the first, the basis for this plane. So far, so good. Questions up to this point? Now, the thing is that's okay, but we want them to be orthonormal just to facilitate the fact that we wouldn't need like to put like an inverse here. So to make them orthonormal, what do? We have to use this Gram-Schmidt method to like create like an orthonormal basis. If you remember Gram-Schmidt, let's see. The first vector is always the first vector in the basis just rescaled by its length. Okay, that's what the method said. The length of the first vector is just 1. That vector was already a unit vector to begin with. That's actually the vector parallel to the x-axis, the one that you would usually call I or E1. So this just gives you 1, 0, 0. So there's nothing that was needed to be done for this first vector. And if you go to the Gram-Schmidt algorithm, which you should definitely write in your formula sheet because like it's kind of hard to memorize, but like the formula for the second vector was something like this. That making sense? In fact, let me start writing them as column vectors because that's how I'll need them for the matrix. I'll write them as column vectors. So now I chose an example which was relatively simple in the sense that these two vectors were already perpendicular to begin with. That doesn't have to happen all the time. It's just because of my choice of the plane that was kind of like a fun, like useful accident. So since these two vectors are perpendicular to begin with, this projection goes away. You won't, because this projection, if you remember, involved like a dot product. So because of like this particular case, you end up with U2 divided by its length. And the length of this vector is root of 2 if you use Pythagoras theorem. So you get 0, 1 over root of 2, 1 over root of 2. Is that okay? So far, so good? And now this is the orthonormal basis we're after for W. So that's good to go. Now we only have to find a basis for W per. Questions up to this point? Yeah. Well, I divided it by root of 2. It's 1 over root of you mean like
Perpendicular, so it doesn't matter how.
right, like here, like since the original vectors were perpendicular to begin with, then to make an perpendicular basis, you only have of like one, you just have to worry about rescaling each vector. That's what I'm trying to say. Is that okay?
And you know, perpendicular because dot product.
Right. If you do the dot product, you'll find that it's 0. Yes. In fact, like if you want them drawn out, U1 is kind of parallel to the x-axis, right? And U2 is along the line y equals x. That's how these two vectors look on this picture. So that's kind of that's why it makes sense for these two to be perpendicular, because one is kind of like telling you the direction along which you drag the line to make the plane, and the other is kind of like giving you the direction of the line. Is that okay? Okay. You see, like, well, hopefully you realize how many steps each of these problems have. One of the other reasons why I'm just putting 8 problems in the final, because sometimes I'll give you like pieces of data so that you don't have to do everything from scratch. But I'm just doing everything from scratch because so that you see all the steps involved. But sometimes I may give you like, well, a basis for one vector space is this, or things like that, so that you don't have, or like very simple numbers, so that it's like they're not hyper long computations, because every of these things does require a lot of like calculation of things and tools. So let's see what's basis for W. W perp, sorry. For W perp, remember the idea is to make a matrix whose rows are the basis of W. It doesn't matter if you use like orthonormal basis or the regular basis, like it's just easier to work with those numbers. Right, so you make a matrix whose rows are the vectors of W, and you reduce it. There's nothing to reduce in this matrix. It's already good to go. So what's the null space of this matrix? That requires x to be 0 and y plus z to be 0. So y is minus z, right? So if you take a vector x, y, z, it is 0 minus z comma z. So it's z times 0, negative 1, 1. So the basis for we're getting orange. So the basis for W perp is this vector U3, which again, like if you ever take multivariable calculus, that's what's called a normal vector to this plane, which you can just read out from the entries of the plane, because you move all the variables to one side, and that gives you the coefficients of the equation, gives you the normal vector. But that's like kind of how you can also do it this way. And this should be orthonormal. It is for free perpendicular to these two vectors, because this vector space is supposed to be perpendicular to this one. So you don't have to worry about anything involving perpendicularity. The only thing that you have to worry is about making this of size 1, because that's not guaranteed. So if you take, what we should take is B3 to be U3 divided by its length. So you end up with 0 minus 1 over root of 2, 1 over root of 2. And that's the third vector. Is that okay? And okay, this is very fun. See what happens. Now we go back to this formula for the projection. The projection has to be Q. Q is a matrix of eigenvectors, so you just copy paste these vectors as column vectors. So you put 1, 0, 0, 0, 1 over root of 2, 1 over root of 2, right? And then you put the last one that we just found. So you put here 0 minus 1 over root of 2, 1 over root of 2. Okay, that's the matrix Q. Then you have to put the diagonal matrix, right? Since we had two vectors from W, you have to put 2 ones, right? Because they're from W, they're their own projection. And since you have a vector from W perp, you put a 0. Does that make sense? So far, so good? And then finally, you just transpose the matrix Q. So transposing the matrix Q gives you, it's almost the same. It's 1, 0, 0, 0, 1 over root of 2, minus 1 over root of 2, and then 0, 1 over root of 2, 1 over root of 2. So this is Q transpose. Okay. Far so good. Questions about this?
If you know use of us.
Oh, what to put here, you mean? The thing is, like, these two belong to W, so they're their own shadow. That means they were rescaled by 1, right? Because nothing happened to them. And that's why they correspond to eigenvalues 1.
Oh, okay.
And this, because it belongs to B perp, the shadow of it disappears, vanishes, right? So it was rescaled by 0. I mean, kind of was multiplied by 0. That's what I'm trying to say. So since it was multiplied by 0, you put like a 0 here. So it's always a 1 for each vector of W and a 0 for each vector of W perp. Does that make sense? Any other questions about this? So if you do this multiplication of 3 by 3 matrices, it's not too bad because there are a bunch of zeros in the formula, but still it's not like, you do have to be careful to make sure that you find the correct answer. You find 1, 0, 0, 0, 0, 1 half, 1 half, 1 half, 1 half. That's the, when you multiply those 3 matrices, that's a matrix that represents the projection. Is that making sense? So you can see it's symmetric. If you do a square, you'll get this matrix back again. But what's more important is just to see what it does to a vector. So what should be PW times the vector? Let me see if I can write it here. So what happens if you multiply this matrix by a vector? It should give you the shadow, right? That's what we were after at the end of the day. So what's the first entry of this multiplication? When you do that? Yes. What's the second entry? Y plus E over 2, right? What's the third entry? Y plus E over 2, right? So let's think that this actually makes sense. Well, let me give you a second to copy this, and you'll see that it actually is a good formula. the condition for being in this vector space was that the last two entries of the vectors should be the same, right? If you do notice what this matrix did was, well, I don't know what X, Y, and Z are. So the matrix astutely just is like, well, I will just average these two numbers out and I use them as their new two last entries, right? So what this matrix is doing is averaging out the last two entries to make them the same number. And by being the same number, now you belong to the vector space. And since X didn't appear in this equation, I don't care what happens to X, so I'll leave it alone. And that's why the matrix doesn't touch X. That making sense? So it's like I mean, it is a smart, I mean, it's not like a silly formula that you get. Once you see it, you kind of realize, oh yeah, this is what you should have expected all along. And it's like kind of like the most democratic way to do the formula because you just consider Y and Z are kind of like the same. Because like if you look at this equation, there's no difference between Y and Z. They both appear multiplied by the coefficient 1. So the matrix kind of like takes that into account and averages them out in the more naive way. So in fact, like you even see here, like this is also what's called like a probability matrix because all the rows and columns add up to 1, right? Like the row, like if you add up the entries of the rows, you get 1, 1, 1, and you add up the entries of the columns, you get 1, 1, and 1. And that's these matrices then show up in probability theory because if you see the formula, it was averaging out things. Okay, and also like probabilities are between 0 and 1, and 0 and 1 are the eigenvalues of these matrices, right? So it's all connected at the end of the day. Okay, isn't that cute? So yeah, it's a nice example to see like everything very concretely. But the point is that if you had a 10-dimensional vector space, then you can do the same. You find a basis for this 10-dimensional vector space, you find a complement, you find the basis for that, you make up with a corresponding matrix, blah, 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 blah. And then you would have like a projection for that. Okay, any questions about this? Yeah.
So it's a good way to think of the PW, that is basically a matrix that takes any vector and makes it applicable, make it for that vector space.
Right. It forces it to belong to the vector space, right? In a way that's kind of like you know. Let's see, where do I have a vector? You have a vector, right? You want it to belong to this vector space. The matrix kind of will force it to be here in the most like less violent way. Like a violent way would be like, well, you just drag this vector around, like just rotate it, do whatever you want and destroy all the information. But this matrix is kind of trying to do it in the most like, I just want to touch you as little as possible so that you belong to the vector space. I mean, you can make that more precise because there's like a minimization property going around here. So there's like a distance from the vector to the plane. Again, and you're minimizing the distance formula. So it's like a Lagrange multiplier problem because there's a constraint or whatever. So there is like an optimization. I mean, you can show that this is actually the best way to do it if you want to minimize the distance between the original vector and the shadow vector. So it's not like just like you just like randomly, forget about what the vector is. So you're trying to do it in the most gentle way to force it to belong to that space. Does that make sense? But yeah, so there's some calculus around. Like there's another way to find this formula using calculus. So you literally set it up as a max mean problem, and you're trying to minimize like the a distance formula. In fact, that actually brings me. Okay, so this won't be on the final, but it's like a good, nice thing to mention because it's related to this. So yeah, I'll just put this. This is for fun for people to know that that's actually how many things are. This is how matrices many times are used in practice. So how can you always solve a system of equations? So if you remember a system of equations, how did I write a system of equations at the very beginning of the semester? well, I wrote it as AX equals B, right? That's like almost, well, that's almost how the course started. AX equals B. Right, so if you remember a system of linear equations, that it had three possibilities. Either there's like a unique solution, infinitely many solutions, or no solutions, right? So what I'm trying to say is like, is there a way to do something to this so that there's always at least one solution, right? So how can I get rid of the inconsistent case? Okay, so let's try to think about when was it that this system could be solved? B had to be a linear combination of something. Had to be a linear I mentioned this briefly once, or a couple of times, but this system of equations can be solved if you can express B as a combination of what? Yeah, the columns of A, right? Is perfect. So you'll see where we're headed with this. So that means another way to say it is that B must belong to the column space of A. That's almost by definition. So what actually is happening, if you think about it more geometrically, is that the column space is a vector space. So it really does look like a plane or something else, right? So you have a vector space, which is the column space, right? And you have this vector B, right? So in general, the vector B may not belong to the column space, so that's why you cannot solve the system, right? But well, that looks awfully familiar to that, right? So what you can do, like, is well, the best next thing you can do is like find this shadow on the column onto the column space. So you project it, right? And almost like, but it's almost like a circular argument. This forces the vector to be in the column space, so that automatically guarantees the solution. So what you can always solve is AX equals the projection onto the column space of B. Okay, so this can always be solved by almost by definition. Is that making sense? And that's more or less the idea behind these least squares methods and other things that I mentioned, because if you think about what a least squares method is, like if you have ever done like a laboratory class or like physics or chemistry or whatever, you have like a set of measurements that you make, right? You may want to find like a curve that fits that data as much as possible, like that in the best way. You shouldn't expect like a perfect match, because like every measurement has some uncertainties and things like that. So maybe there's not necessarily like a curve that will pass literally through all of these points. But if you write out the condition of a curve that passes through all of these points, it's kind of like solving a system of linear equations, depending on how you set it up. So it's kind of like you end up with a system of linear equations, which you necessarily shouldn't expect to solve perfectly. So instead of solving it perfectly, you solve it with the projection thing. And that in a sense is the best possible way to solve it because of this error thing that I mentioned. So that goes back to all this, like, approximation methods. And so from there, like, this is also related to data analysis or image analysis, because again, maybe you have trained like a computer on some data set, and you want to find, if you want like a picture, you want to, oh, is it a cat or a dog or a pony or whatever. And so you cannot, like, there might be some parameters that say, well, after this threshold, like it will be a pony, or if it has its values, this range of values, it would be a cat or whatever. And so you want to make, like, you may want to see like what's the subspace that this is closest to, or things of that sort. So you could set it up as some sort of like, projection problem. Like you're trying to project, like you want to see Or you want to see what happens if you kind of like filter the image or do other things to it. Okay, so again, I won't ask you that, like, I won't ask this, because, it's not, basically, once you have the projection matrix, you just multiply it by the vector you care about, and then you just solve the system. So it's, but it's kind of theoretically useful to know that that's how things work. So on Wednesday, I'll do a review. As I said, I'll do a different review on the other class. I'll also record that one. And then on Monday of next week, which is our official, our last class, you can just come if you still have questions or whatever, but I won't teach any more new material neither Wednesday nor Monday. Okay, so in terms of material, we are done. But yeah, I'll still see you. Just take the announcement if you want to take a look at the problems that we review before coming to class, but if not, you can just come